Okay, we're going to go ahead and get started as those quizzes are being passed out. Nate and I are team teaching today, so I'm going to spend the first 10 minutes or so getting you guys up to speed, and then we'll have Nate take you through identifying HOMO and LUMO in organic molecules. So, last time we were talking about bonding in hydrogen, and we had gotten to the point where I said that you can think of the sigma bond in hydrogen as coming from end-on-end overlap of a 1s orbital on the first hydrogen with a 1s orbital on the next hydrogen. And that sigma bonding orbital looks like this. And most of the time, electrons in this sigma bonding orbital would tend to spend their time in between the two nuclei. And this bonding orbital is lower in energy or more stable than the 1s atomic orbital that each hydrogen started with. And there's two reasons why a bonding orbital is more stable than the atomic orbital that you start with. One is potential energy. That is, an electron gets to experience two positively charged nuclei instead of one. So, and because of Coulomb's law, you know that negatively charged electrons are attracted to positively charged nuclei. Okay, so, and in general, closer to the nucleus is going to be lower in energy. The second issue is a kinetic energy issue. This comes out of the math, and you don't need to know the math, but the conclusion from the math is important, which is electrons that are spread out in space have lower kinetic energy than those that are highly localized. And an electron, let's see, somebody in the middle still needs a quiz. All right, so anyway, electrons that are spread out in space are more stable than those that are highly localized, and when you bond, you get to spread out in more space, over more space than when you're just on an isolated atom. Okay, so bonding orbitals are lower in energy. So far that tracks pretty well with what you learned from valence bond theory last time. The second thing though, the new thing is that MO theory requires us to consider antibonding orbitals. And these come from the out-of-phase combination of the two orbitals. We'll call this antibonding orbital a sigma star, and it basically comes from subtracting one of the s orbitals from the other. Conceptually, what this looks like is you're going to bring together hydrogen A with hydrogen B, and you're going to bring them together with opposite wave function sign. And as they approach each other with opposite wave function sign, the wave function is going to cancel out where the two overlap. That's destructive interference. And in fact, if we draw what this sigma star antibonding orbital looks like, there is a node or a place where wave function equals 0 in between the two nuclei. Just as we saw with our standing wave examples last time, an orbital that has nodes in it, a wave function that has nodes in it, is always higher in energy than a wave function that does not have nodes in it. So we'll see that the sigma star antibonding orbital is higher in energy than the 1s atomic orbitals that we started with. And again, the reasons for that, one reason for that is electrons, if there were electrons in this antibonding orbital, they would spend their time sort of on the outside, away from the space between the two nuclei, and farther from the nuclei is higher in energy. So this concept of antibonding orbital is new, though you've encountered it as you've read the study guide. What is an antibonding orbital? It is simply a higher energy state that an electron could adopt. Both the bonding orbital and the antibonding orbital, both the sigma and the sigma star, are solutions to the Schrodinger equation for the hydrogen atom, and one of them is lower in energy than the other. Okay? So we can actually diagram this out to have a clearer picture of what we're talking about here. And as we do, it'll become clear why hydrogen bonds in the first place. Without a bond, you just have two isolated hydrogens, HA and HB, and the electron on each of those would be in a 1s orbital, isolated, experiencing only one nucleus. If the two come together, we form both the sigma bonding orbital and the sigma star antibonding orbital. I've shown you what the sigma bonding orbital looks like. It looks like basically a football enveloping both the hydrogen and both hydrogens. And I've shown you what the sigma star antibonding orbital looks like. It looks like a dotted line in between to indicate the place where the node is, and then there are oppositely shaded lobes on each of the hydrogens, and those lobes are leaning away from the space between the two nuclei. All right, yes?
So do you have to account for both types of bonding because you don't know what kind of spin the electrons have and also what the base sign is?
Okay, so do you have to account for both types of bonding because you don't know what spin the electrons have? You do have to account for both types of orbitals, bonding and antibonding. It has nothing to do with spin. So the wave function phase or sign is simply whether the wave function has positive or negative magnitude at a point in space.
And that doesn't relate to spin.
And that has no relation at all to spin. Yep. So, and I've chosen, in fact, we're mostly going to ignore spin. The rule is 2 electrons can occupy the same orbital if they have opposite spin. If they don't, they can't, but we won't really encounter that or worry about it. Yes?
So it's explaining that like the electrons are better between the two bonding because what causes the nodes and antibonding? Like why would that be favorable if it's more?
Right, so what causes the node in the antibonding orbital and why would that be favorable? And your reasoning that why would electrons want to go there in the first place? You're right, they don't. So these two orbitals are created by the fact that the two hydrogens come close together, but because each hydrogen only has one electron, we only fill the bonding orbital, and the antibonding orbital is empty. Okay, and this is an important point. With a covalent bond, we're always now, from here on out, going to think a covalent bond has a filled bonding orbital, but there's still an empty antibonding orbital present. The antibonding orbital is simply the next high energy state that an electron could adopt if it got promoted there, or if I added another electron to the molecule. Antibonding orbitals are really tricky. Think of it as a higher order harmonic on a vibrating guitar string. It's there, but the lowest energy state is the bonding orbital, okay? So the bond strength is this difference in energy between the bonding orbital and sort of our break-even point, which is the energy level of the starting atomic orbitals. This is the energy that is released when you form a bond, okay? And this is the energy you have to put into a system to break a bond. It turns out the antibonding orbital is higher in energy than that break-even point, and that difference in energy from the break-even point to the antibonding orbital is actually bigger than the difference in energy for the bonding orbital. And because, you know, I want to deal with magnitude and not actual signs of energy differences, it's mathematical scrupulosity. Those are absolute value bars, okay? Just don't worry about them. I just need them to be there, okay? So this energy gap here between the break-even point and the antibonding orbital is a little bit bigger than this energy gap between the bonding orbital and the break-even point. Which means if I promoted an electron from the bonding orbital to the antibonding orbital, what would that do? What does it do if I have an electron that's now more destabilized than the other one is stabilized? Go ahead.
Would the covalent bond break?
Yeah, the bond's going to break because now you are worse off on average than you would have been had the bond never existed. Your break-even point is what the energy looks like if the bond never existed. If this one up here is higher in energy than this one is below, then the benefit of the bond is gone and the molecule flies apart. Yes?
I didn't catch with the two, the purple and
So this energy difference is between the bonding orbital and the break-even point. This is how stable the bond is. This is the benefit of the bond. This energy difference is just simply how high above that break-even point is the anti-bonding orbital. And this pink energy difference is bigger than the black energy difference. Which, go ahead.
A lower difference energy more stable?
I think you may be misunderstanding me a little bit, but it's tricky. With energy, lower in energy is more stable. Higher in energy is less stable. Okay? So if I were to measure how stable this orbital is, it's lower in energy than this break-even point, so it's more stable. Similarly, the anti-bonding orbital is less stable than the break-even point. Now, we're dealing with energy differences here, so I'm going to try to say it as clearly as I can. The anti-bonding orbital is more destabilized than the bonding orbital is stabilized. So what that means is if I promote an electron to the higher energy level, I now cancel out the bond and I even make it worse. Does that make sense? That's actually going to be a general point in this class. If you populate an antibonding orbital, either by promoting an electron to the antibonding orbital or by taking 2 electrons from some other source and dumping them into that antibonding orbital, you're going to break the bond. Yes?
Does that apply even if there's 2 electrons in the sigma and only 1 electron in the sigma star?
Right, so what if you have 2 electrons in the sigma and you come along and you reduce the molecule by adding an electron and you put it in the sigma star? Well, then you've offset the bond partially, but not completely. So it's not as stable as it was, but it's not completely broken. We won't have I can't think of an example in OChem where we'll do that. Yeah?
So is the change in energy between like the antibonding and the break-even point always bigger?
Yeah.
Is the change in energy like for all?
Yeah, that's general. The antibonding orbitals are always more destabilized than the bonding orbitals are stabilized. And that is why putting electrons in them breaks bonds.
So then why do some bonds not happen? Like,
Okay, so why do some bonds not happen? Let me demonstrate that. I think it's a great question. Let's imagine for a moment that instead of hydrogen, we're dealing with helium. We have a helium A and we have a helium B. How many electrons does helium have? 2. So each helium starts with 2 electrons. Now the rule here is that you figure out what the orbitals are going to look like first, and then you fill them up with the available electrons. So if I had 2 heliums come together at this distance, I could expect a sigma bonding orbital and a sigma antibonding orbital to be solutions to the Schrodinger equation at that distance between the 2 atoms. Now let's fill up the available orbitals. I would fill up the bonding orbital, and I would also fill up the antibonding orbital, right? And then what happens? There's 0 benefit to bonding. The 2 heliums are like, ew, and they move apart from each other. That is why, this is, folks, the origin of the octet rule and of the valence shell rule for helium. This is why helium's a noble gas. It's not that it can't possibly make a bond, it's that if it does, the antibonding orbital is filled too, so who cares? It falls apart. Go ahead.
So I would like a helium-hydrogen bond not be
Right, so now what if, and your problem set actually asks you to consider this, what if instead of helium, let's use 1 helium, and then let's use 1 hydrogen, and actually, let's not let it be a hydrogen atom, let's just let it be a proton, a positively charged hydrogen, empty, right? Put those 2 together, you can fill the bonding orbital and keep the anti-bonding orbital empty. So you guys just predicted that you could make a molecule that would look like this. It actually exists in interstellar space. It's not particularly stable because it's positively charged, but it's it's reasonable. Okay, so you can use antibonding orbitals to predict whether things can bond and what's going to happen in a reaction. Yeah.
Would it be reasonable for like a non-positively charged hydrogen, just like a regular hydrogen to bond with helium?
Okay.
Antibonding.
We're playing what if today, which is kind of fun. So you want to do helium and hydrogen atom. That would do this and this. Are we sufficiently confused? That would be like adding, so you would partially fill the antibonding orbital. It's not going to be that stable. It's not going to be as stable. It's going to be basically half a bond. Yeah. Yes?
But since it's not stable, but it's still not gonna break because they're not full regardless.
I mean, I can't predict it. I don't actually know. You would say that it's worth half a bond, and so however, so that bond would be more prone to break than just a regular full bond,
So less stable but not broken.
but not broken. Yeah. Okay. Yes.
Is it common for atoms to stay in an antibody state, or is it more of a transitionary state?
So is it common for atoms to have populated antibonding orbitals? No. You'll see actually though that, I mean this is kind of an aside, but if we go back to the blue case, which is just two hydrogens, whatever, there, you'll see that if I had another way that I can promote an electron from sigma to sigma star is simply by absorbing light. So if I had a photon of light of the right wavelength, it can excite an electron to a higher energy state. And that electron can fall back down immediately, releasing a photon. This is actually how fluorescence works. And this is actually also how vision in your eyes work. We're going to talk about that later, but the fact that you can see now is because a molecule in your eye is accepting a photon of light, being promoted to a higher energy level, and then there are downstream events after that that get converted to an electrical signal in your brain. So yeah, this kind of thing happens all the time. Yes?
Are you recording right now?
Am I recording now? Yes. Sweet. All right. Yes.
So when you're talking about that going to an antibonding is a cause of like having higher energy, it's that because they are more unstable in the antibonding, that is the source of being at higher energy. Is that accurate?
That's right. Being higher in energy is the same thing as being less stable. So being in an antibonding orbital is destabilizing because, by definition, the antibonding orbital is so high in
So
energy.
it's not necessarily like adding an electron adds energy, it's that it like makes it more unstable and therefore has more energy.
Let me think about that question for a moment. I mean, there are two ways you can fill an antibonding orbital. One is to add energy by promoting an electron from here to here. The second way is to add an electron. Now, that's purely theoretical at this point. I'll give you some examples of how that happens. Yeah. Okay. So with that in mind, the fact that antibonding orbitals exist, we're now prepared to think about organic molecules in a slightly different way. And this is just going to be a small tweak on what we've already talked about last time. So last time we looked at ethylene and we said, I expect those carbons to be sp2 hybridized. And we said that the sigma bond between the carbon and the hydrogen comes from what orbital on carbon? What atomic orbital is involved in sp2, right? Did we not talk about that last time, or did we? We did. Okay. All right. That's something to review. So a carbon that is sp2 hybridized has 3 sp2 orbitals, and then left over unhybridized is a p orbital, and that is its alphabet of 4 atomic orbitals. So the sigma bond comes from overlap of an sp2 orbital on carbon with a 1s orbital on hydrogen. The carbon-carbon sigma bond comes from overlap of an sp2 orbital on carbon with an sp2 orbital on the other carbon. And for each carbon, we can check off the 3 sp2 orbitals involved in those 3 sigma bonds. And then lastly, we have the pi bonding orbital, and where does that come from? Which 2 atomic orbitals contribute to the carbon-carbon pi bond? The p orbital, 1 on each, right? And if you were to draw that, what it would look like is a large lobe enveloping both of the two carbons above the plane of the page. This is the overhead view. Shading here indicates one wave function sign. There's a node in the plane of the page, and then there is another lobe below the plane of the page that has opposite mathematical sign, okay? And sometimes that's difficult to view or understand, so sometimes we'll draw the side view. Either view is totally fine, so you can pick the one that you like. From the side, the pi bonding orbital would look like this, and because we like complete representations, it's also totally fine to draw that pi bonding orbital just as though you just had two p orbitals there side by side. In other words, all three of the drawings of the pi orbital that I've done just in the past few seconds, those are all equivalent. These are all okay drawings of a carbon-carbon pi bond. Okay, that's the bonding orbital. Now let's talk about the antibonding orbitals. This is what we haven't dealt with. Okay, so we'll start with pi because we've drawn things. Antibonding orbitals come from overlap of orbitals with opposite wave function signs so that there is a node in between the two atoms. So what would we expect a pi star to look like? You'd expect it to look like two p orbitals side by side but with opposite wave function sign, and you would expect there to be a node in between the two. Okay, that is a place where wave function goes to 0. If I were going to draw this pi star on the overhead view of the molecule, what would it look like? Well, there's going to be a node in between the two atoms, and it would basically look like I have two p orbitals, one on each carbon, only we've got opposite wave function sign. Now remember, this is a drawing of what the antibonding orbital looks like, and we're going to call it the pi star. This is not two separate p orbitals together. This is one pi star antibonding orbital. And for the pi bond, the electrons are going to be in the pi bonding orbital, which is going to be filled, but the pi star is going to be empty. All right? So now when you see a molecule, you need to think each filled bonding orbital has an empty associated antibonding orbital in the same space, occupying the same space, but at a higher energy level. It's simply the higher energy waveform that an electron could adopt. That's true for the sigma bonds as well. So let's just go, I thought I saw somebody wanting to say something. Okay. So let's look real quickly at what the sigma bonding orbitals are going to look like. And then we'll also, well, actually, fine. For ethylene, a carbon hydrogen sigma bonding orbital is going to simply look like an sp2 orbital that enveloped the hydrogen. That's what you get when an sp2 orbital overlaps with a sphere. So that's what the sigma bonding orbital looks like. How about the sigma star? What would the sigma star look like? Just sort of drawn on the same molecule. A sigma star or an antibonding orbital is always going to have a node in between the two atoms. On the hydrogen side, it's just going to look like a sphere that's leaning away from the node, and it's leaning because it's been canceled out towards the node. Then on the carbon side, it basically looks like a backwards sp2 orbital. You have the small lobe pointing towards the node, small because it's been canceled out, and then a larger lobe pointing away from the node. That's what a carbon-hydrogen sigma star antibonding orbital looks like. Then let's just talk briefly about the carbon-carbon bonding orbital. That's the one between the two carbons in the middle in ethylene. Overlap of the two sp2 orbitals generates the sigma carbon-carbon bonding orbital. That's going to basically look like a football in between the two nuclei with small lobes pointed outward. This is overlap of the large lobe of the two sp2 orbitals on each carbon. And then how about the sigma star, carbon-carbon sigma star antibonding orbital? As before, it's easiest to start with the node in between the two atoms. All antibonding orbitals have a node. Small lobes pointing towards the node, small because they've been canceled out, and then larger lobes pointing away from the node. So it essentially looks like some backwards sp2 orbitals that are pointing away from each other. So this is what all the orbitals in the molecule look like. Bonding orbitals that are filled and antibonding orbitals that are empty. Yes?
I'm trying to understand the antibonding and then the sigma carbon-carbon specifically. I can understand like the sigma being like a huge oval or like the antibonding being like two balls that like have a node between. But I don't get the fact that there's three for the sigma antibonding and then three for the rest of the
I don't think I understand your question. Maybe I
like,
do.
Each area of the donut, like what's your, like what are you drawing? Like is the orange like where you can get one?
No, so the color represents the sign of the wave function. And every time the color changes, it's like a cosine or a sine wave going from positive to negative. So all of this just draws the electron wave for you. And if you want to think, okay, orange means positive, pink means negative, that's fine, as long as you understand that that's sign and not charge. So the electron is positive here, negative here, then positive here. So it's just going through zero twice.
Okay. Oh,
Positive,
each
negative,
stack could be
positive,
like-
negative.
Each stack could be like a weird looking F2.
Yep.
Okay.
Okay. Yes?
Did you say that the carbon hydrogen sigma bond, the large lobe completely covers the F1s?
The large lobe completely covers the 1s. Yeah. Yep. Yes?
So for the carbon-carbon sigma bond and sigma antibond, do the like orbitals on the section on the outside, do those get bigger in the antibond?
Yeah, and I don't have a really good explanation why, but yes, the lobes pointing outward in the antibonding orbital always get bigger. Don't know why. It's the math. Yep.
Would any like carbon heteroatom sigma star look kind of like the carbon-carbon?
Would any carbon heteroatom sigma star look like the carbon-carbon sigma star? In other words, if we were drawing a carbon oxygen or a carbon chloride sigma star, it's going to essentially look like this. Yes. Yep. Yes.
So, sorry, but all, like, both electrons are simultaneously and everywhere that's colored at the same time?
In a bonding orbital, yes, the electrons are simultaneously in everywhere that's colored at the same time.
And the antibonding
Antibonding orbitals are empty. Yep, because there's no electrons there. Yeah.
For different atoms bonded together, can you know, like, how we determine whether it's antibonding or bonding?
Can you say the first part of the question one more time?
Or just like you were carbon-carbon that bond right?
Yeah.
How did you know that it was antibonding?
So the one on the right is antibonding. You know that it's antibonding because it has a node in between the two nuclei.
Okay.
Did I misunderstand?
No.
All right. Yes?
Are there two nodes on the pi antibonded?
Are there two nodes on the pi star?
Yeah.
Yes. So anytime the wave function changes in sign, that's a node. Now notice that the pi star has a node in the plane of the sigma bonds. As you go from above the plane of the sigma bonds to below, wave function sign changes. It turns out that node is also present in the pi bonding orbital. So I'm highlighting the new node that happens when you go from pi to pi star. Both of them have this same node in the plane of the sigma bonds. You'll notice something similar with the sigma bonding orbitals. sp2 atoms, sp2 orbitals always have a node at the carbon. So the sigma bonding orbital for carbon has basically two nodes, whereas the sigma star has 1, 2, 3. I'm only highlighting the one, the new one, that's different between the two. Does that make sense? Okay, now let's rank these in energy. And you're already prepared to do this based on things we've talked about. So ethylene has basically 4 carbon-hydrogen sigma bonds and 1 carbon-carbon sigma bond, and it's got a pi bond. Which of those options do you suspect is highest in energy or least stable? We got a controversy. Some of you are saying sigma. Some of you are saying pi. Let's clarify. I'm not talking about antibonding orbitals. I'm talking about bonds. Which bonding orbital is highest in energy? Pi. Okay, we're now agreeing because of peer pressure. Let's explain why we're agreeing. Why is a pi bond higher in energy than a sigma bond? 2 ways you can tell. Go ahead.
So the first thing, pi bonds are farther away from the nucleus. The farther away they are, the more energy they
Yep,
have.
good.
And so because they're farther away and they need the overlap still, it's going to take more energy for them to have that pi bond.
Okay, farther from the nucleus, exactly. That is one reason why the pi bond is higher in energy. There's one more that you could think about. Go ahead.
Well, if you think about it mathematically, right, you have the sp orbitals, which are a combination between the s and the p orbital, but the p is always higher than
Good.
the s, which will naturally lower the average energy, and therefore an s orbital by itself, which makes it pi bond, will naturally always be higher in energy.
Good, good. So yes, because the sigma bonds come from orbitals that have s character in them, they are necessarily lower in energy than the pi orbitals. Good, okay. So closer from the nucleus, that's closer to the nucleus, farther from the nucleus. Sigma bonds are closer to the nucleus. They're always lower in energy. Now, some of you are going to be worried about whether the 4 identical carbon-hydrogen sigma bonding orbitals are the same or different or higher or lower in energy than carbon-carbon bonding orbitals. There is an answer to that, and it doesn't matter for most purposes. And the reason it doesn't matter is because we're going to be always worried about the orbital that's highest in energy. And in this case, because the pi orbital is higher in energy than any of the sigma orbitals, we can basically ignore the sigma orbitals. Let's say that again. We're going to care most about the most reactive electrons in a molecule. And in a molecule like this, where there are pi electrons, the sigma electrons aren't necessarily going to matter that much. If this molecule was to react, the most reactive electrons in the molecule would be the pi electrons and not the sigma electrons. So it's actually insignificant from our perspective whether the carbon-carbon sigma bond is more or less stable than the carbon-hydrogen sigma bond. There is an answer to that. You could calculate it, but I don't care what the answer is because it doesn't practically matter for our purposes. Does that make sense? So in a molecule, and again, I'm going to highlight this break-even point, we're going to care most about the electrons that are in the highest occupied molecular orbital, which in this case is going to be the electrons in the pi bond. Now, in organic chemistry, molecules that have a high energy pair of electrons are called nucleophiles. They are called nucleophiles because they love the other phile for philos from the Greek love, and then nucleo meaning nucleus. Nucleophiles are nucleus lovers. They have a high energy pair of electrons that they wish could be lower in energy, and the way it could be lower in energy is if they share that pair of electrons with another nucleus. A nucleophile is also a Lewis base. You've heard that term before. A Lewis base, you learned in general chemistry, is an electron pair donor, and I'm guessing that made no sense to you. It certainly didn't to me when I was in general chemistry. What is it, like throwing electrons at somebody else? No, it's not that at all. In fact, a Lewis base has a high energy pair of electrons that it would like to share with another atom so they can be in a bond, so they can move lower in energy. So for nucleophiles or Lewis bases, we're going to care about which electrons are most reactive, that is highest in energy. And that is going to be the electrons in the highest occupied molecular orbital. So if ethylene, this alkene, this molecule with a pi bond, were to act as a nucleophile or a Lewis base, which electrons in it would be the most reactive electrons? Which would be the HOMO? Pi. Okay, you all have a quiz in front of you. Go to problem 1. We've changed the molecule a little bit. I look at that and I'm like, oh, I already know the answer. But that is because I am old and have experience. You look at that one. Do we need some more quizzes? Anybody need one? You look at that, and because it's different, you're not sure what to do with it. I want you to look at that molecule, figure out all the bonds that are there, rank them in energy, figure out which pair of electrons is highest in energy, decide what the HOMO is, and then draw it on that molecule. I will give you 2 minutes. Okay, I'm going to interrupt your talking. How many of you are worried about the bonds between the carbon and the methyl groups, the carbon-carbon sigma bonds there? Excellent. Why are you not worried about them? Because they're always lower in energy than the pi bond. Are you seeing a principle? If there's a pi bond, you now know what to focus on immediately. So what is the HOMO of this molecule? Pi, right? It's the carbon-carbon pi bond. Now, if I'm going to draw it on this molecule, what do? I draw a lobe above the plane of the page and below the plane of the page if it's drawn like this. What if, now I know that you need some reassurance, so what if you chose to draw it like this? Is that okay? Yeah. What if you chose to draw it like this? Is that okay? Yeah. Just fine. What if you chose to draw it like this and you're like, okay, I'm just going to draw the p orbitals leaning kind of like this to communicate that some of them are above the plane of the page and some of them are below. That's actually also okay. We can tell what you're thinking. All right? The one thing that would sort of not be okay here, the one thing that would sort of be bad would be if you communicated in your drawing that you think that the p orbitals are, it's subtle, right? But if you communicate in your drawing that you think those p orbitals are in the plane of the sigma bonds, that they're actually in the plane of the page instead of above and below, then you're confused, and that's the wrong conclusion. All right? So your drawing needs to communicate. And honestly, on an exam, a multiple choice exam, you're not going to be drawing anything. You're going to be selecting among options, so you need to be able to recognize what a pi bond looks like from multiple perspectives. Okay, questions you want to ask about that? Yes?
If we did it like that when we did the dotted lines across from it, would that work, or should we just always put it on our name? Just because.
If you did it like what? Sorry.
Well, you just erased it where they were like, as if they were in the same thing, but you did dotted lines across.
So,
Or does it really matter? It really doesn't.
I mean, if it makes sense to you and somebody who reads it, I suppose that's okay. All right?
It doesn't really matter.
Okay. All right, so that's an example of identifying HOMO versus LUMO. Now, we need to go back and to think about the empty orbitals. So it turns out, and this is useful, if you can rank the bonding orbitals, you already know the rank of the antibonding orbitals. It's just backwards. It's a reflection. So just as the just as the pi orbital is high in energy relative to the sigma bonding orbitals, so the pi star is lower in energy relative to the sigma star antibonding orbitals. What this means is if you can rank the bonding orbitals, you automatically know that the antibonding orbitals, which are above the break-even line, the antibonding orbitals, are a reflection of the bonding orbitals. And this lowest empty orbital we're going to call the LUMO, the lowest unoccupied molecular orbital, or the LUMO. Now for nucleophiles, we're not going to care about the LUMO. For nucleophiles, we're only going to care about the highest occupied molecular orbital. But for electrophiles, the LUMO becomes very important. Electrophiles are Lewis acids. They are electron lovers. They are electron pair acceptors. Now that doesn't mean that somebody's tossing electrons at the electrophile. That means they have a low energy empty orbital that could accept a pair of electrons and make a new bond. Okay? So for electrophiles, we're going to care about the LUMO. So identifying HOMO and LUMO is important. Go ahead.
So, but if we're filling an empty anti-bonding orbital, isn't that bad? Like, why is that for the bond?
So you just made a prediction, which is if an electrophile accepts electrons into an antibonding orbital, that should make a new bond, but it should also break an old bond. And that's exactly what we'll see, and therein lies all the chemistry you will see this year in organic chemistry. Boom, right? The first and great commandment of OChem is nucleophiles attack electrophiles, and the second is like unto it. The HOMO of the nucleophile attacks the LUMO of the electrophile. When HOMO attacks LUMO, you make a new bond, and if that LUMO is an antibonding orbital, you also break an old bond. It's that simple. Yes?
So will the bond only happen if the HOMO is higher in energy than the LUMO?
Great question. Will the bond only happen if the HOMO of the nucleophile is higher in energy than the LUMO? It doesn't quite have to be higher in energy. It needs to be close enough. Yes?
So when it comes to molecules that don't have any pi bonds, we're supposed to just assume that all sigma bonds are equal to each other in energy?
For a molecule that doesn't have any pi bonds, do we assume that all the sigma bonds are equal in energy to you, to each other? We will show you how to recognize sigma bonds that are weak enough to break and which are higher in energy than others. That's coming. Yes?
So quick question, if you have a molecule that has, let's just say, a double bonded O and a DR attached to it, and it wants you to find the HOMO on them, the electronegativity, the one that's more electronegative, is lower in energy.
So you're dealing. I'm kind of unclear on the example, and I'll tell you what. At this point, I'm going to punt on that because we will deal with examples like that in 352, and it will make more sense then. Oh, also, I'm hoping that you guys read the email I sent you about the problem set. We're just now getting to where you can do some of the problems 6 through 8. So we're going to put those on next week's problem set. They're not going to be graded. Today's recitation sections and tomorrow's are going to focus on just the first 5 problems. We're going to do that regularly as we adjust the pace of the class to what we need here, okay? So don't stress out if you haven't been able to do, and if you didn't know that before now, read your dang email, okay? It goes to your student account. It has to. BYU makes me do that. Yes?
So, I'm trying to figure out the way you would explain the correlation between like having a HOMO and then using a Lewis base. So is it basically like molecules that have a high energy oxide on the molecular orbital are likely to be a Lewis base? Are they always on?
Yeah, so the question is, I think what you're getting at is, when I look at a structure, how do I know whether it would be a nucleophile or an electrophile? Some molecules are almost always nucleophiles, some are almost always electrophiles, some can be both depending on context. This is why on the problem set, I didn't make you decide whether it was going to be a nucleophile or an electrophile. I basically gave you enough hints that you could figure it out. You're going to get that with context and experience. Let's see. What I want to do just in the last couple of minutes is take you to an example from your quiz. I'm telling you that this molecule can be an electrophile. One thing I haven't said is that it can also be a nucleophile depending on context. So I want us to look at this and decide if it's going to act as an electrophile, what the LUMO is. So to determine that, let's look at the bonding orbitals. You have 2 carbon-carbon sigma bonding orbitals. You have 6 carbon-hydrogen sigma bonding orbitals, and you have a carbon-oxygen sigma bonding orbital. You also have a carbon-oxygen pi orbital. So of those available bonding bonds, which do you think has the lowest energy antibonding orbital? Pi star, always. Carbon-oxygen pi star. Okay, that's great. Now, and so if this molecule were to act as an electrophile, the place where it would get attacked is the pi star. So if we draw that pi star on the molecule, you draw a node in between the 2 nuclei. You draw a large lobe on this carbon and another lobe on the oxygen. You'd shade them opposite because there's a node in between. And then you would show the lobes that are below the plane of the page, as is the case for all pi-type orbitals. Okay? That's what the pi star looks like. Now, for right now, I want you to notice that the pi star is on both the carbon and the oxygen. But a nucleophile that it's going to attack can only attack in one spot. So we need to decide, and we're not going to decide today, we need to decide which of those 2 gets attacked. And I want you to be thinking about that. Yes?
Do non-binding lone pairs go into this at all?
Yep, non-bonded lone pairs. You noticed I ignored something. There's lone pairs on the oxygen. So if we were thinking about this molecule as a nucleophile, what are the highest energy electrons in the molecule? So you may be tempted to say it's the pi bond, and you are right that the pi electrons are higher in energy than the sigma bonding electrons. But higher still are those electrons that are not involved in a bond. Necessarily, lone pairs are higher in energy than all of the bonding orbitals. So if you have lone pairs, that's the HOMO. And that's true for this molecule as well. Okay, so we need to stop there. On Friday, you got 2 options here. We're not done with that quiz. You can keep it and bring it back Friday. Or if you want credit for having been here today, time served, you can turn it in up at the front on your way out. I don't care. We'll keep working on the quiz next time. All right, and Nate, my student, is going to lead you through some more examples of this next time.